Hi, folks. This time we're going to talk a little bit about electromagnets. We've been talking about the relationship between electricity and magnetism, and one of the niftiest illustrations about this relationship are electromagnets. Now, an electromagnet is a magnet that is produced when an electric current flows through it. The simplest form of an electromagnet is some sort of a piece of metal, a metallic core or a magnetized core, surrounded by a coil of wire. When the current is going through that piece of wire, a magnet is produced. When the current is no longer there, something is not magnetized. So the nifty part of an electromagnet is that it is a magnet that you can turn on or off. And it has gazillions of different applications. This very simple electromagnet is the sort of electromagnet that is typically produced in a lab. And in our labs, we're going to make something very similar to that. Low voltage power supply, a iron core like a nail, a bolt, something like that, simple piece of wire wrapped around it, and then it becomes magnetized and you can pick up small bits like paper clips. To determine the north or south polarity of an electromagnet, there are left-hand rules and there are right-hand rules. We're going to talk about the left-hand rule, and the left-hand rule is the direction of negative current flow. So we're going to talk about electrons flowing. Talk to your instructor. If you are dealing with positive current flow, then you are going to use the right-hand rule. But in this particular course, we're going to be dealing with negative current flow, so we're going to use that left-hand rule. So this is how this works. If the electrons are coming out of the negative terminal of the battery, and I'm going to draw a simple battery here, or wet cell, or dry cell, and if they're coming out of the negative terminal and going through the coil of wire this direction and then going to the positive terminal of the battery there, that's going to coil round and round and round your core. If you take your left hand and you coil your fingers in the direction that the current is flowing around that core, the direction that the wires are coiled, then your thumb, your lovely thumb, is going to point towards the north magnetic pole. So it is a way to predict what is going to be the north and the south pole of the magnet. If you are using positive current, you use your right-hand rule and everything will be reversed. The strength of an electromagnet can be changed, so it is very versatile. You don't have to try and guess or buy the right magnet at the right period of time. You can alter the strength of an electromagnet on the fly, and that can be changed by the current. You put a different current through the electromagnet, and you can change its strength. You can actually change its polarity if you flip it from one polarity to another with a switch in a circuit. The number of turns of wire. If you have a few turns of wire, it's going to tend to be very, very weak. If you put lots more turns of wire, you are going to make a stronger magnet. And the type of core. If you have a small core, it's going to have a tendency to be weaker. If you give it a larger, more substantial core, more of those iron atoms with domains that can be lined up, you're going to end up with a stronger electromagnet. So there's lots of versatility when you're machining, designing, engineering something. Uses of electromagnets. I'm going to give you a few examples, but there are, like I mentioned, gazillions of them. One of the most visual and extreme are separating iron from other things in a scrapyard. And I used to drive by one when I was a kid. There was one that was a few miles from my home, and I just was fascinated by these huge, massive cranes. If they have a whole pile of scrap and they want to get out the iron and not pick up the plastic and not pick up the aluminum or other bits and pieces, the electromagnet's going to pick up the magnetized bit, leave the other rubbish behind, because it's only going to be attracted to the magnetic material. Lots of the bells and buzzers, everything from your doorbell to the little buzzer that says beep, your food is done, and many appliances are a electromagnet. For example, your doorbell, you push on this, it is going to send a small supply of current that is going to make something magnetic, which will be attracted and ring a bell. Very simple, but the simplest designs are often the ones that perpetuate for hundreds of years. Music speakers. Music speakers, you have electricity that comes in. There is a permanent magnet here. There is a coil of wire there. And as the electric current comes through this coil of wire, this is all attached to this paper cone. Of course, this is a cutaway diagram. And to respond to the electrical signal, which is carrying the signal that corresponds to the music that is coming through, the speaker cone is going to oscillate out and in and going to move these air molecules, creating compression waves that will eventually come to your ear that you are going to respond to as sound. Microphones work very much the same way, but the whole thing is in reverse. The sound waves come in, causing a little diaphragm to move, creating an electric current within a magnetic field, and that electric current is picked up, amplified, and ta-da, you have a microphone. Magnetic levitation trains, not a lot of them running around the United States, as many as there are, for example, in Japan, but these are really nifty things. By changing the polarity of the current, they can change whether something is attracted or repulsed. And so by changing the polarity of the track and the train, they can keep it accelerating forward. And that constantly alternating current will keep that train moving forward. Nifty technology. Don't want to spend a lot of time talking about it this second. Another one that's common, and many of you may have had an MRI at some point in your life. MRI stands with magnetic resonance imaging. In your body, you have a lot of water molecules. Water molecules contain hydrogen atoms, and these hydrogen atoms, of course, all contain little spinning electrons. Because they're electrons, they are unpaired. One electron, and as we know, an unpaired electron is the world's tiniest magnet. So what happens is the electrons in your body are all oriented in all sorts of different wacky directions, all higgledy-piggledy. What happens in an MRI is they put it into a very, very strong magnetic field. It makes all these hydrogen electrons go into one direction, orient them all in one direction in the strong magnetic field, and then they bounce back. When they bounce back from the strong magnetic field, they emit a tiny itty-bitty radio frequency. We're talking itty-bitty amounts of RF, little bits of radio frequency. Those little bits of radio frequency are picked up. It depends on if you're dealing with something that is very dense, like bone, or softer tissue, or something that is water inside of your body. But because of the density of material that is traveling through, these different RF signals can be translated into an image, and it gives us amazing pictures within the human body. So electromagnets, they are one of the wonders of the modern age.